Take a moment and look around you. Perhaps you're sitting in your favorite chair after a long day. Maybe you're lying in bed with the lights turned low, letting the quiet settle around you before sleep. Everything feels still. The walls aren't moving. The floor beneath your feet feels solid. Your coffee cup rests peacefully on the table. From every ordinary perspective, you seem completely motionless. But what if I told you that, at this very moment, you are racing through the universe at nearly 388 kilometers every second? Not every hour, not every minute, every single second. Before you finish listening to this opening, you will have traveled tens of thousands of kilometers through space. By the end of today's journey together, you will have moved hundreds of thousands of kilometers without taking a single step, without hearing a sound, and without feeling the slightest hint of motion. It sounds impossible, yet it is one of the most remarkable truths modern astronomy has revealed. Our everyday experience teaches us to associate motion with sensation. When a car accelerates, we're pushed gently into our seats. An airplane lifting off the runway vibrates beneath us. A speeding train hums along its tracks. Every movement we know comes with some physical reminder that we are changing position. Space doesn't work that way. The Earth spins on its axis at remarkable speed. At the equator, the surface moves at roughly 1,670 kilometers per hour. At the same time, our planet circles the Sun at nearly 30 kilometers every second. The Sun itself is orbiting the center of the Milky Way at well over 200 kilometers every second. And the Milky Way is moving through the universe even faster still. When all of those motions are combined, our galaxy, and everything inside it, is traveling through space at roughly 388 kilometers per second relative to the cosmic microwave background, the oldest light in the universe, and you are making that journey with it. If you've been listening for only 30 seconds, you've already crossed more distance than many spacecraft travel during their first days after launch. Pause for a moment and let that settle in. Without realizing it, you've already traveled farther than the distance separating many countries on Earth. Before this session ends, you will have moved a distance approaching that between Earth and the Moon, yet your body insists that you have not moved at all. Why? The answer reveals one of the deepest principles in physics. Motion by itself cannot be felt. Only changes in motion can. Imagine sitting inside a perfectly smooth train with no windows. The ride is silent. There are no bumps, no vibrations, no sudden turns. If the train moves at a perfectly constant speed, you would have no experiment you could perform inside that carriage to determine whether you were moving or standing still. Everything around you shares the same motion. The air moves with you. Your chair moves with you. Every atom in your body moves together. There is no wind rushing past because Earth's atmosphere is traveling with the planet. There is no sensation of speed because the floor beneath you, your home, your city, your continent, and the entire Earth all share the same cosmic journey. From your own perspective, you are perfectly at rest. It is only when we step outside our everyday frame of reference, when we compare ourselves to the oldest light left over from the birth of the universe, that we discover just how astonishing our motion truly is. For thousands of years, humanity believed the heavens were fixed and eternal. Ancient civilizations watched the stars move slowly across the sky and imagined the Earth standing quietly at the center of creation. Even after we learned that Earth orbits the Sun, it was tempting to picture our solar system drifting peacefully through an otherwise calm universe. Reality turned out to be far stranger. The universe is not a collection of isolated objects sitting in empty space. It is alive with motion. Stars orbit galaxies. Galaxies orbit clusters. Entire clusters of galaxies flow through an immense cosmic landscape, shaped by gravity on scales almost impossible to imagine. Our Milky Way is part of that enormous migration. It is not wandering aimlessly through the darkness. It is heading somewhere. That realization emerged only after astronomers began studying one of the oldest signals in existence, the faint afterglow left behind by the Big Bang itself. When they carefully measured this ancient light, They expected it to appear nearly identical in every direction. Instead, they discovered something extraordinary. The light appeared ever so slightly warmer in one direction and slightly cooler in the opposite direction. The difference was incredibly small, but it carried enormous meaning. It revealed that our entire galaxy was moving through this ancient sea of light. At first, scientists assumed the explanation would be simple. Perhaps this was merely the result of the universe expanding. Perhaps nearby galaxies were tugging on us through gravity. Perhaps the motion could be explained by everything already known about our cosmic neighborhood. But as more precise observations accumulated, the numbers refused to cooperate. Every calculation left something unexplained. The Milky Way wasn't simply drifting with the expansion of space. It was moving too fast. And even more puzzling, it was moving toward one specific region of the sky. Something enormous appeared to be pulling us. Not just our solar system, not just the Milky Way. Entire groups of galaxies seemed to be sharing this same mysterious destination. Imagine standing beside a wide river. At first glance, the surface appears calm. But after watching carefully, you notice leaves, branches, and entire logs all drifting steadily in exactly the same direction. You naturally begin asking the same question any curious observer would ask. Where is the current leading? The galaxies of our universe behave in much the same way. They are not scattered randomly across space. They are following an invisible current. And somewhere ahead lies whatever is creating that current. For decades, astronomers struggled to understand what could possess enough gravitational power to influence not merely a single galaxy, but hundreds of thousands of them across hundreds of millions of light years. The answer would eventually transform our understanding of the universe itself. But before scientists could identify what was pulling us, they first had to solve an even greater mystery. They had to prove that this invisible destination was real. If you're enjoying this journey into the hidden architecture of our universe, consider subscribing to the channel and turning on notifications. We explore the biggest questions in astronomy, cosmology, and the history of science through calm, immersive storytelling designed to inspire curiosity long after the video ends. Because in the next chapter, we'll discover how a faint whisper of light left over from the birth of the universe revealed that our entire galaxy is speeding towards something so massive that for decades, scientists simply called it the Great Attractor. The idea that our galaxy is racing through space sounds almost unbelievable. If someone had made that claim a century ago, it would have been dismissed as little more than speculation. After all, how could anyone possibly measure the motion of an entire galaxy? There are no road signs in space, no fixed landmarks beyond the universe itself. Everything appears to be moving relative to everything else. So how did astronomers discover that the Milky Way is traveling in one particular direction? The answer begins with the oldest light that still exists. Long before there were galaxies, stars, planets, or even atoms, the universe itself was a very different place. Nearly 13.8 billion years ago, the cosmos was unimaginably hot and dense. It wasn't an explosion into empty space, as it is often described, but the rapid expansion of space itself. In those earliest moments, temperatures were so extreme that matter as we know it simply could not exist. Electrons and atomic nuclei flew freely through an ocean of energy. Photons, the particles of light, were trapped in an endless game of cosmic pinball. Every time a photon tried to travel even a tiny distance, it immediately collided with another charged particle. It scattered, changed the direction, and collided again. The young universe was not transparent. It was more like standing inside an impossibly thick fog, where light could never travel farther than a few centimeters before disappearing into the haze. For nearly 380,000 years, this was the nature of reality. Then something extraordinary happened. As space continued expanding, the universe gradually cooled. Eventually, the temperature dropped enough for electrons to combine with atomic nuclei, forming the first stable hydrogen and helium atoms. Suddenly, there were far fewer free charged particles to scatter light. For the first time in cosmic history, photons were free. Light that had been trapped since the beginning of time suddenly burst across the universe in every direction. Those very same photons are still traveling today. For almost 14 billion years, they have crossed an expanding universe, stretching along with space itself. Once brilliant enough to glow like the surface of a star, they have cooled into faint microwave radiation that fills every corner of the cosmos. Astronomers call this ancient afterglow the cosmic microwave background, or simply the CMB. You can think of it as the oldest photograph ever taken. Not a photograph of Earth, not a photograph of the Milky Way, but a photograph of the universe itself when it was only 380,000 years old. A newborn compared to its present age. Every direction we look in the sky reveals this ancient light. Whether we point a telescope toward distant galaxies, empty darkness, or the opposite side of the heavens, the CMB is always there, surrounding us like a faint cosmic wallpaper left behind by creation itself. When scientists first detected this radiation in 1965, it became one of the greatest discoveries in modern astronomy. It provided powerful confirmation that the Big Bang had really happened. More importantly, it gave researchers something they had never possessed before, a universal frame of reference. Unlike stars and galaxies, which are all moving in different directions, the cosmic microwave background comes from everywhere at once. It is the oldest observable light in existence, arriving from every part of the universe almost equally. If we were perfectly motionless relative to this ancient radiation, the CMB would appear exactly the same in every direction. That was the expectation. Reality turned out to be far more interesting. As increasingly precise satellites mapped the microwave background across the entire sky, astronomers noticed an incredibly subtle pattern. One half of the sky appeared ever so slightly warmer. The opposite half appeared ever so slightly cooler. The temperature difference was astonishingly small, only a few thousandths of a degree above absolute zero, but it was unmistakable. At first glance, this might seem insignificant, yet it carried one of the most profound messages the universe has ever delivered. The explanation comes from a phenomenon familiar to almost everyone, even if we rarely think about it. Imagine standing beside a highway as an ambulance approaches. While it races toward you, the siren sounds higher in pitch. As it passes and speeds away, the tone suddenly drops lower. Nothing about the siren itself has changed. What changes is the wave reaching your ears. This is known as the Doppler effect. The exact same principle applies to light. When an object moves toward a source of light, the light waves become slightly compressed, shifting toward shorter wavelengths and higher energies. Astronomers call this a blue shift. When an object moves away, the light waves stretch out, becoming longer and lower in energy. This is known as a red shift. The cosmic microwave background behaves in exactly the same way. If our galaxy is moving toward one region of the sky, the ancient light coming from that direction becomes slightly compressed, making it appear just a tiny bit warmer. In the opposite direction, where we are moving away, those same microwave wavelengths become stretched, making the radiation appear slightly cooler. The warm side, the cool side. Together they create what astronomers call the CMB dipole, a subtle fingerprint of our motion through the universe. This wasn't simply a curious observation. It was a measurement, a remarkably precise one. By calculating the size of this temperature difference, scientists could determine not only that we were moving, but also our speed and our direction. The numbers were astonishing. The motion wasn't coming from Earth's rotation. Subtract that, and the signal remained. It wasn't caused by Earth's orbit around the Sun. Remove that as well, and the pattern was still there. It wasn't even the Sun's journey around the center of the Milky Way. After accounting for every known motion inside our local neighborhood, one unmistakable conclusion remained. The Milky Way itself was moving. Our entire galaxy, containing hundreds of billions of stars, countless planets, immense clouds of gas and dust, and perhaps trillions of unseen worlds, was traveling through the universe together. This was not the motion of one planet, not the motion of one star, not even the motion of one solar system. It was the motion of an entire galaxy. Imagine watching a single leaf floating down a river. At first, you might assume only the leaf is drifting. Then you notice the branch beneath it is moving too. Soon you realize the entire river is flowing toward the same destination. That is what the cosmic microwave background revealed. We were never observing the movement of Earth alone. We had discovered that the river itself was carrying us. Even more astonishing was the fact that this motion pointed toward one very specific region of the sky. It wasn't random. It wasn't chaotic. Our galaxy wasn't wandering aimlessly through the universe. Something was influencing its path. Something massive enough to tug not only on the Milky Way, but, as astronomers would soon discover, on thousands upon thousands of other galaxies as well. The ancient light left behind by the birth of the universe had revealed the first clue. It told us that we were moving. The next question was far more unsettling. What, exactly, were we moving toward? The discovery of the cosmic microwave background answered one question, but it immediately created another that was even more unsettling. Yes, the Milky Way was moving. Yes, scientists could measure its speed with remarkable precision. But why was it moving that fast? Motion, after all, always has a cause. For astronomers, this became one of the greatest detective stories in modern science. The first suspect seemed obvious. The universe itself is expanding. Ever since Edwin Hubble made his groundbreaking observations in the 1920s, scientists have known that galaxies are generally moving away from one another. The farther away a galaxy is, the faster it appears to recede. This relationship became known as the Hubble flow, the large-scale expansion of space itself. Imagine raisins inside a loaf of bread as it bakes in the oven. The raisins are not crawling through the dough. Instead, the dough expands, carrying every raisin farther from every other one. That is essentially what the universe is doing. Space itself is stretching. At first glance, this seemed like the perfect explanation. Perhaps the Milky Way's motion was simply another consequence of cosmic expansion. But when astronomers carefully performed the calculations, the numbers refused to agree. The expansion of the universe certainly explained part of our observed motion. It just didn't explain all of it. There was an extra velocity, a large one, that remained completely unaccounted for. Scientists then turned their attention closer to home. Perhaps another nearby galaxy was pulling us. The obvious candidate was Andromeda. Our nearest large galactic neighbor lies about 2.5 million light-years away and contains roughly 1 trillion stars. Together, the Milky Way and Andromeda are the dominant members of what astronomers call the local group, a small family of more than 50 galaxies bound together by gravity. In fact, Andromeda and the Milky Way are already falling toward one another. Billions of years from now, the two giant spiral galaxies are expected to merge, creating a single enormous galaxy. Surely such a massive neighbor must account for our mysterious motion. Again, the calculations told a different story. Andromeda's gravity certainly influences us, but only by a relatively modest amount. It simply isn't massive enough to accelerate an entire galaxy to the speed astronomers were measuring. The mystery remained. If not Andromeda, then perhaps the answer lay farther away. Beyond the local group sits the Virgo Cluster, an enormous gathering of more than 1,000 galaxies located roughly 55 million light-years from Earth. Compared to anything in our immediate neighborhood, Virgo is a true giant. Its combined mass is almost beyond imagination. For decades, many astronomers believed Virgo must be the dominant gravitational force shaping our corner of the universe. Once again, the equations were carefully assembled. Distances were measured. Galaxy masses were estimated. Gravitational forces were calculated using Einstein's theory of general relativity. Virgo certainly contributed, Its enormous gravity pulled on our local group exactly as expected. But once all the numbers were added together, something astonishing became clear. Virgo explained only part of the observed motion. A significant amount remained completely unexplained. So astronomers looked even farther. They included neighboring galaxy clusters. They mapped surrounding superclusters. They accounted for every major concentration of matter they could observe. Each new calculation improved the picture slightly. Each new observation filled another small piece of the puzzle. Yet no matter how many known structures they included, the final answer always came up short. It was as though someone had carefully balanced every force acting on an airplane, only to discover that an invisible engine was still pushing it forward. Something important was missing. At this point, scientists faced only two possible conclusions. The first possibility was deeply uncomfortable. Perhaps our understanding of gravity itself was fundamentally wrong. That was not an attractive option. Einstein's general theory of relativity had already survived countless experimental tests. It accurately predicted the motion of planets, the bending of light around massive objects, gravitational time dilation, gravitational waves, and even black holes, decades before they were directly observed. Abandoning general relativity would require extraordinary evidence. The second possibility seemed equally extraordinary. Perhaps gravity wasn't wrong. Perhaps something unimaginably massive simply hadn't been discovered yet. An enormous concentration of matter could naturally explain everything. It would pull not only the Milky Way but every nearby galaxy toward itself. The missing velocity would no longer be mysterious. The mathematics pointed toward exactly that conclusion. Somewhere in the direction of the constellations Centaurus and Norma appeared to be an immense gravitational source, whose influence extended across hundreds of millions of light-years. Astronomers did not yet know what it was. They only knew its fingerprints. Like detectives arriving at a crime scene, they could not see the suspect, but they could clearly see the tracks left behind. Those tracks were written into the motions of galaxies. Every galaxy became another clue. Every measured velocity pointed toward the same region of the sky. Eventually, researchers gave this invisible gravitational giant a simple name: the Great Attractor. It sounded almost mythical. Something hidden, something colossal, something powerful enough to influence entire galaxies without ever revealing its face. Early estimates suggested an almost incomprehensible mass. Not millions of suns, not billions, not even trillions. The Great Attractor appeared to represent a gravitational region containing the equivalent of tens of quadrillions of solar masses, far beyond anything previously imagined as a single cosmic structure. Numbers like these challenge human intuition. Our Sun outweighs Earth by about 330,000 times. The Milky Way contains hundreds of billions of stars. Now imagine thousands upon thousands of galaxies, together with enormous quantities of invisible matter, all contributing to one vast gravitational basin. That was the scale scientists were beginning to suspect. Even more astonishing was the number of galaxies apparently responding to its pull. This wasn't a local phenomenon affecting only our cosmic neighborhood. As astronomers expanded their surveys, they noticed that galaxy after galaxy shared similar motions. Then hundreds, then thousands. Eventually, the evidence suggested that hundreds of thousands of galaxies, spread across a region more than 500 million light-years wide, were drifting in roughly the same direction. Picture standing on a mountaintop after heavy rain. Tiny streams appear everywhere. At first they seem unrelated, but as you watch longer, every trickle, every creek, and every river gradually bends toward the same valley below. The rivers never communicate with one another. They simply obey the shape of the landscape. Astronomers began to suspect that galaxies behave in much the same way. Gravity had carved an invisible landscape across the universe. Galaxies were not wandering randomly through space. They were flowing downhill. The Great Attractor appeared to be the deepest valley in our region of the cosmos. There was only one enormous problem. If something this massive truly existed, astronomers should have been able to see it. Structures containing thousands of galaxies should blaze brilliantly across the sky, yet whenever telescopes pointed toward the predicted location, they found almost nothing. No gigantic supercluster, no impossible black hole, no obvious cosmic monster waiting in the darkness. It was as though the universe had hidden one of its greatest secrets behind an invisible curtain. For years, scientists knew precisely where to look. They simply couldn't see what was there. The mystery was no longer just what the Great Attractor was. The mystery had become something even stranger. How could something powerful enough to move hundreds of thousands of galaxies remain almost completely invisible? By now, the evidence had become impossible to ignore. The Milky Way was moving far faster than expected. Hundreds of thousands of neighboring galaxies appeared to be flowing in the same general direction. Every new observation strengthened the case for an enormous gravitational source hidden somewhere beyond our local cosmic neighborhood. And yet, when astronomers aimed their most powerful telescopes toward the predicted location, they found almost nothing. This was the most frustrating part of the mystery. Imagine hearing the roar of an enormous waterfall somewhere deep inside a forest. You can feel the cool mist on your face. The ground beneath your feet slopes steadily downward. Every stream around you flows toward the same unseen destination. You know the waterfall must exist. Every clue points toward it. But no matter where you stand, a towering wall of trees blocks your view. That was exactly the situation facing astronomers during the late 20th century. Gravity was telling them something extraordinary lay ahead. Their telescopes refused to show it. For years, some scientists wondered whether the Great Attractor was simply an illusion created by incomplete data. Perhaps the measurements were wrong. Perhaps the calculations contained hidden errors. Perhaps there was no mysterious gravitational giant at all. But each time observations became more precise, the invisible pull remained. The mystery wasn't disappearing. It was growing stronger. The problem, as it turned out, wasn't the universe. The problem was our point of view. We often imagine the Milky Way from those beautiful illustrations seen in books and documentaries, a graceful spiral galaxy floating alone against the blackness of space. But we never experience that view ourselves. We live inside the Milky Way. Trying to map the universe from within our own galaxy is a little like trying to draw the layout of an entire forest while standing in the middle of its densest thicket. Nearby trees block the view of everything beyond them. The Milky Way itself became the obstacle. Our galaxy is roughly 100,000 light-years across and contains hundreds of billions of stars arranged within a relatively thin rotating disk. Between those stars lies an enormous amount of gas and microscopic dust, raw material from which future generations of stars will eventually form. To human eyes, this disk appears as the beautiful glowing band stretching across the night sky that we simply call the Milky Way. Beautiful though it is, that glowing band hides a serious problem. The dust scattered throughout our galaxy is astonishingly effective at blocking visible light. Each individual grain is unimaginably tiny, often smaller than a single micrometer, but spread across tens of thousands of light years. Those particles form an immense curtain that absorbs and scatters light arriving from beyond the Milky Way. Looking through it is like trying to observe a distant mountain range through thick smoke. The mountains haven't disappeared, you simply cannot see them. Astronomers eventually gave this hidden region an appropriate name. They called it the zone of avoidance. Not because galaxies actually avoid that part of space, but because for decades, our telescopes appeared to find remarkably few galaxies there. It was an illusion. The galaxies were present all along. They were simply concealed behind our own galactic disk. Then came the remarkable coincidence that made the Great Attractor even more mysterious. The invisible gravitational source seemed to lie almost directly behind this very curtain. Out of the entire sky, The one region scientists most desperately needed to observe happened to be the one region our own galaxy hid from view. It was cosmic bad luck on an almost unbelievable scale. Imagine spending decades searching for an enormous city, only to discover that your own house has been blocking the window the entire time. That is precisely what had happened. Astronomers possessed indirect evidence that something extraordinary existed beyond the zone of avoidance. Yet conventional optical telescopes were almost useless. The universe had not hidden the Great Attractor. Our own galaxy had. For years, researchers could estimate its direction. They could calculate its approximate distance. They could estimate its enormous gravitational influence. But they could not see the structures responsible for that influence with ordinary visible light. Many scientific mysteries end there. This one did not. Instead of giving up, astronomers asked a different question. What if visible light wasn't the right tool? After all, the universe communicates in far more than the narrow band of colors our eyes can perceive. Human vision evolved to detect only a tiny slice of the electromagnetic spectrum. Beyond the familiar rainbow lie radio waves, infrared light, ultraviolet radiation, X-rays, gamma rays, and many other forms of electromagnetic energy. Each reveals a different face of the universe. Perhaps some of those invisible wavelengths could penetrate the curtain of dust. That idea changed everything. Radio waves, with their much longer wavelengths, interact very differently with tiny dust particles. Instead of being scattered and absorbed, many radio waves simply pass through the dust almost unhindered. Infrared light offered another breakthrough. Although shorter infrared wavelengths can still be affected by dust, longer infrared wavelengths penetrate much deeper into regions completely opaque to visible light. Suddenly, astronomers possessed entirely new eyes. Beginning in the 1980s and continuing over the following decades, radio observatories and infrared sky surveys slowly began mapping the hidden universe behind the Milky Way. What they discovered was astonishing. The zone of avoidance was not empty at all. It was crowded. One hidden galaxy appeared, then another. Soon dozens emerged, then hundreds. Eventually thousands of previously unknown galaxies were revealed, quietly occupying the very region that had seemed almost blank on earlier maps. Entire galaxy clusters appeared where astronomers had once believed there was only darkness. It was as though someone had switched on the lights inside a room everyone had assumed was empty. The universe beyond our galaxy suddenly became far richer than anyone had imagined. Even more intriguing, these newly discovered galaxies were not scattered randomly. Many belonged to enormous interconnected structures stretching across millions of light years. The hidden landscape behind the Milky Way began to take shape, and with every new observation, one realization became increasingly unavoidable. The Great Attractor was probably not a single gigantic object. It seemed to be something far more complex. Perhaps astronomers had been asking the wrong question from the very beginning. Instead of wondering, what is the Great Attractor? Maybe they should have been asking, what kind of cosmic structure could generate a gravitational pull this immense? The answer, when it finally emerged, would force scientists to rethink not only the Great Attractor itself, but the architecture of the universe on the largest scales ever explored. Because hidden behind the dust was not one monster waiting in the darkness. It was an entire hidden landscape, one that would eventually reveal that our galaxy is only a tiny traveler within a vast cosmic network far greater than anyone had imagined. By the late 20th century, astronomers had finally managed to peer through the Milky Way's curtain of dust. What they found was remarkable, but it wasn't what anyone had expected. For years, the phrase, "the Great Attractor," had inspired dramatic images. A colossal black hole, hidden in deep space, an unimaginably massive object swallowing everything around it, or perhaps an exotic cosmic phenomenon unlike anything ever observed. Reality turned out to be both less dramatic and far more profound. The Great Attractor wasn't hiding because it was invisible. It was hiding because scientists had been looking for the wrong kind of object. As new infrared and radio surveys revealed thousands of previously unseen galaxies, astronomers noticed something unexpected. There was no single giant object sitting at the center of the mystery. Instead, there were galaxy clusters, lots of them, enormous collections of galaxies packed together in a relatively small region of space, each contributing its own gravitational pull. One structure immediately stood out, known today as the Norma Cluster. It lies roughly 220 million light-years from Earth, almost exactly in the direction predicted decades earlier by measurements of the cosmic microwave background. For a brief moment, excitement spread through the astronomical community. Perhaps this was it. Perhaps the Norma Cluster was the long-awaited Great Attractor. After all, it was an extraordinary object, containing hundreds of galaxies, including several gigantic elliptical galaxies many times more massive than the Milky Way. Norma ranks among the richest galaxy clusters in our cosmic neighborhood. If any visible structure could explain the mysterious gravitational pull, this seemed the most likely candidate. But once again, the numbers refused to cooperate. The Norma Cluster was undeniably massive, yet it still wasn't massive enough. Its gravity accounted for part of the observed motion, but not nearly all of it. Even this cosmic giant fell short of explaining why the Milky Way and hundreds of thousands of other galaxies appeared to be flowing toward the same destination. Rather than solving the mystery, Norma simply became another piece of a much larger puzzle. As observations improved, astronomers discovered additional galaxy clusters surrounding Norma. Then more. Some were connected by long bridges of galaxies. Others appeared arranged along enormous strands stretching across millions of light-years. Instead of finding one gravitational monster, researchers were uncovering an entire hidden landscape. Slowly, a completely different picture emerged. Perhaps the Great Attractor wasn't a single object at all. Perhaps it was an entire region of space where matter had accumulated over billions of years. Imagine standing in a vast mountain valley after heavy rainfall. No single raindrop creates the river. No individual stream controls the flow. Instead, countless tiny streams merge together, guided by the shape of the landscape itself. Eventually, they form one powerful current. The Great Attractor seemed to work in much the same way. Gravity wasn't coming from one extraordinary object. It was the combined influence of many enormous structures acting together. Galaxy clusters, superclusters, invisible halos of dark matter, all contributing to one immense gravitational basin. This realization fundamentally changed the way astronomers thought about the universe. For much of the 20th century, galaxies were often pictured as isolated island universes, floating independently through vast empty space. That image was never entirely wrong. It was simply incomplete. As larger and larger surveys mapped millions of galaxies across billions of light-years, another pattern slowly appeared. The universe wasn't random, it possessed structure. On the largest scales imaginable, galaxies arranged themselves into gigantic filaments, stretching across hundreds of millions of light-years. These filaments intersected one another at dense knots where galaxy clusters formed. Between them lay enormous empty regions called cosmic voids. Vast expanses containing surprisingly little matter. Astronomers began calling this immense architecture the cosmic web. The name was remarkably appropriate. Viewed from far enough away, the universe resembles an intricate network of threads. Some scientists compare it to a spider's web. Others see the branching structure of rivers viewed from space. Still others notice an uncanny resemblance to networks of neurons inside the human brain. Despite these visual similarities, the cosmic web wasn't designed by anyone. It emerged naturally. Its origin reaches all the way back to the earliest moments after the Big Bang. Tiny fluctuations in density, differences so small they amounted to only a few parts per million, were preserved in the cosmic microwave background. Over billions of years, gravity slowly amplified those microscopic differences. Regions that were slightly denser attracted more matter. As they gained mass, their gravity became stronger. That stronger gravity attracted even more matter. the process repeated again and again over cosmic time. Meanwhile, regions that began slightly emptier gradually lost more material, becoming the enormous voids we observe today. Like snow rolling downhill into valleys, matter naturally collected along invisible gravitational pathways. Those pathways became the filaments of the cosmic web. Galaxy clusters formed where multiple filaments intersected, and somewhere within one particularly dense intersection lay the region astronomers had been calling the Great Attractor. Suddenly, everything began making sense. The Milky Way wasn't being pulled toward a mysterious cosmic monster. It was moving along one of these gravitational highways. Our galaxy was simply following the natural flow of matter through the universe. The Great Attractor wasn't an object waiting to be photographed. It was a destination created by the combined gravity of countless structures woven together across hundreds of millions of light years. This represented one of the most important shifts in modern cosmology. Scientists stopped asking, "Where is the giant object?" Instead, they began asking, "How is matter distributed across the largest scales of the universe?" The difference was subtle, but it changed everything. Imagine watching leaves floating down a river. At first, you might search for something beneath the surface, pulling each leaf individually. Eventually, you realize no hidden machine exists. The leaves move because the entire river follows the shape of the land. The Great Attractor is much like that. It is not a cosmic vacuum cleaner, dragging galaxies through empty space. It is the deepest part of a vast gravitational landscape, formed over nearly 14 billion years of cosmic evolution. Our galaxy is one leaf among hundreds of thousands, drifting along an invisible current, carved by gravity itself. Yet this revelation led to an even greater question. If the Great Attractor was only one dense region within an enormous gravitational landscape, then what larger structure did it belong to? Like every river flowing into a larger watershed, perhaps the Great Attractor itself was only one feature within an even greater cosmic system. The answer would reveal something extraordinary. It would redefine humanity's cosmic address and show that the Milky Way is part of a structure so immense that astronomers didn't recognize its true boundaries until the 21st century. For generations, humanity has tried to answer one simple question: where are we? At first, the answer seemed straightforward. We live on Earth. Later, we learned that Earth is only one planet orbiting an ordinary yellow star. Then we discovered that our Sun is merely one of hundreds of billions of stars inside the Milky Way. As astronomy advanced, our cosmic address kept growing. The Milky Way became part of the local group, a small family of galaxies stretching roughly 10 million light-years across. Beyond that lay the Virgo Cluster, and for many years astronomers believed our local group belonged to the Virgo supercluster, a vast structure containing thousands of galaxies spread across more than 100 million light-years. For decades, that seemed to be the end of the story. It wasn't. The Great Attractor forced astronomers to look beyond the simple labels they had inherited. Something wasn't fitting together. Galaxies weren't merely sitting inside superclusters like marbles inside a box. They were moving, flowing, following invisible gravitational currents. If gravity shaped these enormous motions, perhaps the boundaries of our cosmic neighborhood should not be defined by where galaxies happen to be located, but by where they were actually going. That subtle change in perspective led to one of the most beautiful discoveries in modern cosmology. In 2014, an international team of astronomers published a new map unlike anything that had come before. Instead of simply plotting the positions of galaxies, they mapped their motions. Every measured galaxy became an arrow. Every arrow pointed somewhere. When millions of these arrows were combined, an extraordinary pattern emerged. The galaxies were behaving almost like raindrops falling across an immense landscape. Some flowed in one direction, others curved gently around enormous structures. Entire galaxy clusters streamed together like rivers, joining larger rivers. And eventually, those rivers converged toward one immense gravitational basin. The astronomers gave this newly recognized structure a Hawaiian name, Laniakea. It means immeasurable heaven or immense paradise. Few scientific names have ever been more appropriate. Laniakea is not simply another galaxy cluster, nor is it merely another supercluster added to an already long list. It represents something much larger. It is a vast gravitational watershed stretching across roughly 520 million light-years and containing more than 100,000 galaxies, including our own Milky Way. Suddenly, humanity's cosmic address became far richer than anyone had imagined. We do not simply live inside the Milky Way. The Milky Way belongs to the local group. The local group belongs to Laniakea, and Laniakea itself is one enormous region within the even larger cosmic web. This was more than a new classification. It was an entirely new way of understanding the architecture of the universe. Imagine standing on a mountain during a gentle rainstorm. Individual raindrops fall randomly onto the landscape. Yet once they touch the ground, their paths are no longer random. Tiny trickles merge into streams. Streams become rivers. Eventually, every drop finds its way toward the same valley below. Now imagine drawing a map, not of where each drop landed, but of where every drop ultimately flows. That map would naturally reveal the boundaries of an entire watershed. Laniakea works in precisely this way. It is not defined by solid borders. There are no invisible walls separating it from neighboring regions of space. Instead, its boundaries are determined by gravity. Every galaxy inside Laniakea is gradually flowing toward the same gravitational center. Every galaxy outside its boundaries is flowing somewhere else. That realization transformed the Great Attractor from a mysterious object into something much easier to understand. The Great Attractor is not an isolated monster hiding in darkness. It is the deepest part of Laniakea's gravitational landscape. It is the point toward which the rivers of galaxies naturally descend. Think back to the image of a river system. No one asks where the river ends. Instead, every river belongs to a drainage basin. The Great Attractor is not the entire basin. It is the lowest point within it. This simple idea resolved decades of confusion. Astronomers had spent years searching for one impossibly massive object because they assumed gravity had to originate from a single source. But gravity doesn't always work that way. On Earth, a valley is not created by one enormous rock buried underground. It exists because the entire surrounding landscape slopes gently toward the same location. Likewise, the Great Attractor is produced by the combined gravity of galaxy clusters, dark matter, and enormous cosmic structures spread across millions of light-years. The universe, it turns out, is less like a collection of isolated cities and more like an interconnected continent. Everything is connected. Everything influences everything else. And we happen to live on one small branch of this immense cosmic network. This new perspective also changed the way astronomers visualize motion itself. For centuries, space had often been imagined as an empty stage upon which galaxies wandered independently. Laniakea suggested something entirely different. The universe behaves almost like a living system. Galaxies flow through invisible channels carved by gravity. Clusters merge like tributaries. Matter streams along gigantic filaments of the cosmic web toward dense intersections where gravity is strongest. Our Milky Way is participating in that journey at this very moment. Every second that passes, our galaxy drifts a little farther along one of these invisible currents. Every star within the Milky Way, including our Sun, shares that motion. Every planet around every star shares it as well. Every living creature on Earth has been traveling this cosmic river for billions of years without ever realizing it. There is something deeply humbling about that thought. Human history spans only a few thousand years. Civilization has existed for only the briefest instant compared to cosmic time. Yet, throughout all of recorded history, our ancestors have been carried together along the same invisible gravitational pathway. Empires rose and fell. Languages were born and disappeared. Entire species evolved, all while our galaxy continued its silent voyage through the universe. Perhaps the most surprising part is that this journey is incredibly slow by human standards and unimaginably fast by cosmic ones. At roughly 388 kilometers every second, we are moving toward the gravitational heart of Laniakea, but the destination still lies about 200 million light-years away. Even traveling at our current speed, reaching that center would require tens of billions of years, far longer than the universe has existed. And yet, there is one final twist. As extraordinary as Laniakea is, and as powerful as the Great Attractor appears to be, gravity is no longer the only force shaping our future. Far beyond every galaxy, every cluster, and every filament, another mysterious influence has begun to dominate the fate of the cosmos. It is invisible, it opposes gravity itself, and in the end, it may prevent us from ever reaching the destination toward which our galaxy has been traveling for billions of years. If the story ended with Laniakea, it would already be one of the greatest discoveries in modern astronomy. Our galaxy is not drifting aimlessly through empty space. It belongs to an immense gravitational watershed stretching across more than 500 million light-years. Together with nearly 100,000 other galaxies, the Milky Way is slowly descending toward the deepest part of that cosmic landscape, a region we know as the Great Attractor. At first glance, the mystery seems solved. Gravity explains everything. Or does it? As astronomers refined their measurements, another puzzle quietly emerged. The visible galaxies inside Laniakea simply weren't heavy enough. Even after adding together the mass of hundreds of galaxy clusters, trillions of stars, vast clouds of gas, and countless planets, the numbers still refused to balance. The gravitational pull inferred from the motion of galaxies was far greater than the amount of visible matter could produce. It was a familiar problem. In fact, astronomers had encountered it decades earlier, while studying the rotation of individual galaxies. Consider the Milky Way. Our solar system orbits the galactic center at roughly 220 kilometers per second. According to Newton's laws, stars farther from the center should move more slowly, just as Pluto travels more slowly around the Sun than Mercury does. But that isn't what astronomers observed. Stars near the outer edges of galaxies were moving far too fast. If only visible matter existed, those stars should have escaped into intergalactic space long ago. Instead, they remained securely bound to their galaxies. Something invisible was holding them together. The same mystery appeared again and again. Galaxy clusters behaved as though they contained far more mass than telescopes could see. Light from distant galaxies bent around invisible concentrations of gravity, creating spectacular gravitational lenses that revealed hidden mass lurking between the galaxies themselves. Even the tiny fluctuations preserved in the cosmic microwave background, the ancient light we explored earlier, could only be explained if most of the universe's matter was invisible. Piece by piece, the evidence pointed toward an astonishing conclusion. The universe is dominated by something we cannot see. Astronomers call it dark matter. Despite its mysterious name, dark matter is not simply ordinary matter hidden in darkness. It does not emit light. It does not absorb light. It does not reflect light. As far as electromagnetic radiation is concerned, it is effectively invisible. Yet, gravity betrays its presence everywhere. Current estimates suggest that ordinary matter, the stars, planets, nebulae, galaxies, and every living thing that has ever existed, accounts for only about 15% of all matter in the universe. The remaining 85% is dark matter. Think about that for a moment. Everything humanity has ever directly observed through telescopes belongs to the smaller portion of the cosmic inventory. The overwhelming majority of matter has never been seen directly. We know it exists only because of what it does. Its gravity quietly shapes galaxies, binds clusters together, and sculpts the enormous filaments of the cosmic web. Without dark matter, the universe we know would never have formed. After the Big Bang, tiny variations in density would have remained too weak for ordinary matter alone to build galaxies within the available time. Dark matter provided the invisible scaffolding upon which ordinary matter gradually accumulated over billions of years. It is the hidden architecture behind the visible universe. That realization transformed our understanding of the Great Attractor. The enormous gravitational basin at the heart of Laniakea is not created solely by the galaxies we can see. Those galaxies are merely the brightest peaks, rising above a much larger invisible landscape. Surrounding every galaxy is a vast halo of dark matter. Entire galaxy clusters are embedded inside even larger halos. The filaments connecting clusters are themselves threaded with enormous concentrations of dark matter stretching across millions of light years. The Great Attractor is therefore not simply a gathering of galaxies. It is a region where visible matter and invisible matter combine to produce one of the strongest gravitational environments in our cosmic neighborhood. Suddenly, the extraordinary mass estimates no longer seemed impossible. The invisible universe had been contributing all along. And yet, just as astronomers were becoming comfortable with this explanation, another discovery overturned expectations once again. Until the late 20th century, scientists assumed that gravity, although perhaps weakened by distance, would eventually slow the expansion of the universe. Imagine throwing a ball into the air. Gravity gradually reduces its speed until it stops and falls back toward Earth. The universe, many believed, should behave similarly. Expansion should gradually slow as gravity pulls everything back together. Perhaps one day expansion would even stop entirely. Then came one of the most surprising discoveries in the history of science. In 1998, two independent teams of astronomers studied extremely distant exploding stars known as Type 1a supernova. These explosions shine with remarkably consistent brightness, allowing researchers to calculate their distances with exceptional precision. The goal seemed straightforward: measure how much the universe's expansion had slowed over time. Instead, they found the exact opposite. The expansion wasn't slowing, it was accelerating. The farther researchers looked into space, and therefore back in time, the clearer the conclusion became. Some unknown influence was pushing galaxies apart faster and faster. Gravity was not winning. Something else was. Scientists gave this mysterious phenomenon another deceptively simple name: dark energy. Unlike dark matter, which adds gravity through its mass, dark energy appears to work in the opposite direction. Rather than pulling structures together, it causes space itself to expand at an ever-increasing rate. Today, dark energy is believed to make up nearly 70% of the total energy content of the universe, while dark matter accounts for about 25%. Everything we can actually see, every star, every planet, every nebula, every galaxy, every human being, represents only about 5% of the cosmos. That realization is almost impossible to fully comprehend. The universe we experience with our senses is only a tiny visible island floating within an ocean dominated by invisible components whose true nature remains unknown. And this brings us back to the Great Attractor. For billions of years, gravity has been drawing the Milky Way toward the center of Laniakea. Dark matter strengthens that pull, providing much of the hidden mass responsible for the enormous gravitational basin. But dark energy is changing the rules. As the expansion of space accelerates, distant regions of the universe are gradually being carried farther apart. A silent competition has begun. Gravity is pulling us inward. Dark energy is carrying the universe outward. Which force will ultimately determine our destination? The answer is one of the most fascinating and perhaps most bittersweet chapters in modern cosmology. Because despite everything we've learned about the Great Attractor, there is growing evidence that the Milky Way may never actually reach it. For thousands of years, humanity believed the universe was quiet. The stars appeared fixed, the constellations seemed eternal. The heavens looked like an unchanging backdrop against which the story of human civilization unfolded. Today, we know something profoundly different. Nothing in the universe is truly standing still. The Earth spins beneath our feet. The Earth circles the Sun orbits the center of the Milky Way. The Milky Way itself travels through space alongside nearly 100,000 neighboring galaxies, all flowing toward the gravitational heart of Laniakea. It is an extraordinary realization. Yet, after everything we've learned, one final question remains: will we ever arrive? At first glance, the answer seems obvious. If we are moving toward the Great Attractor at roughly 388 kilometers every second, then given enough time, we should eventually reach it. After all, gravity has been guiding this journey for billions of years. But the universe rarely follows our intuition. The problem is that the destination itself is not standing still. Everything we've discussed throughout this journey, the Milky Way, the local group, Laniakea, even the Great Attractor, is embedded within an expanding universe. Space itself continues to stretch. Not because galaxies are flying through empty space like bullets across a battlefield, but because the fabric separating them is gradually growing larger. Imagine placing tiny dots on the surface of an uninflated balloon. As you inflate it, every dot moves farther away from every other dot. No dot is actively crawling across the rubber. Instead, the surface itself is expanding. This simple image captures one of the deepest truths of cosmology. Galaxies often behave in much the same way. For nearby galaxies, gravity can overcome expansion. That is why the Milky Way and Andromeda are moving toward one another despite the universe growing larger. Their mutual gravity is simply strong enough. But over much greater distances, the situation changes. The farther two structures are separated, the more important cosmic expansion becomes. The Great Attractor lies approximately 200 million light-years away. On human scales, that number is beyond imagination. Even on cosmic scales, it represents an enormous distance. For billions of years, gravity has slowly drawn our local group toward that immense gravitational basin. Yet while gravity pulls us inward, the universe itself continues stretching outward. For much of cosmic history, gravity held the advantage. Then something changed. As we explored in the previous chapter, dark energy gradually became the dominant influence, shaping the large-scale future of the cosmos. Unlike gravity, which brings structures together, dark energy causes space itself to expand ever more rapidly. It is as though the river, carrying us toward the Great Attractor, has begun flowing against an increasingly powerful current. Imagine walking toward a distant mountain while standing on an enormous moving walkway. At first, your footsteps carry you steadily closer. Then the walkway gradually speeds up beneath your feet. Eventually, you reach the point where every step forward is cancelled by the floor moving backward. No matter how long you continue walking, the mountain never grows any closer. Cosmologists believe something remarkably similar may be happening on the largest scales of the universe. Today, the Milky Way is still moving toward the Great Attractor. The measurements leave little doubt about that, but calculations suggest that cosmic expansion will continue accelerating for trillions of years. As more space appears between enormous structures, gravity will eventually lose its ability to draw together regions separated by hundreds of millions of light-years. Long before our galaxy could complete its journey, the destination itself may recede beyond our reach. In other words, we are falling toward the Great Attractor, but we may never arrive. There is something strangely poetic about that conclusion. For decades, astronomers imagined the Great Attractor as a hidden monster lurking somewhere beyond the Milky Way. They searched for an impossible object powerful enough to drag galaxies across the universe. Instead, they discovered something far more beautiful. The Great Attractor is not a cosmic predator. It is not a gigantic black hole waiting to consume galaxies. It is not an alien megastructure or a mysterious tear in space-time. It is the natural consequence of gravity shaping matter across unimaginable distances. It is the gravitational heart of our cosmic neighborhood. More importantly, it revealed something even greater than itself. It taught us that the universe possesses structure. Galaxies are not scattered randomly through empty space. They gather into groups. Groups assemble into clusters. Clusters connect through filaments that weave together into the vast cosmic web. Along those invisible highways, matter has been flowing since shortly after the Big Bang. Our Milky Way is simply one traveler among countless others. Perhaps that is the true wonder of this story. The Great Attractor is not remarkable because it threatens us. It is remarkable because it helps us understand where we belong. For most of human history, our universe seemed centered on us. Then we learned Earth is not the center of the solar system. Later, we discovered the Sun is only one ordinary star among hundreds of billions. Then the Milky Way became just one galaxy among trillions. Now we understand that even our galaxy is part of an immense gravitational ecosystem extending across more than 500 million light-years. Every scientific discovery has made the universe larger, yet somehow, it has also made it feel more connected. The atoms inside your body were forged in ancient stars. Those stars formed inside the Milky Way. The Milky Way emerged along one filament of the cosmic web. That web grew from tiny ripples preserved in the oldest light of the universe. In a very real sense, your own existence is connected to processes that began nearly 14 billion years ago. And perhaps that is the greatest lesson hidden within the mystery of the Great Attractor. The universe is not a collection of isolated objects drifting through meaningless emptiness. It is an interconnected story. Every galaxy influences another. Every cluster helps shape the cosmic web. Every thread of gravity participates in the evolution of the whole. At this very moment, while you sit quietly watching this video, your planet is spinning. Your sun is orbiting the Milky Way. Your galaxy is gliding through Laniakea. And Laniakea itself is part of an unimaginably vast universe that continues to expand into a future no human being will ever witness. You cannot feel any of this. There is no vibration, no rushing wind, no sensation of extraordinary speed. Yet every second, you are traveling hundreds of kilometers through the greatest landscape we have ever discovered. Perhaps the most astonishing part is not that we are moving. It is that a species living on a small rocky world around an ordinary star has learned to measure that motion, uncover its cause, and trace its place within the grand architecture of the cosmos. The Great Attractor was never simply the destination. It was the clue that allowed humanity to discover its true cosmic home.